Okay, so now we talked about central limit theorems for means, central limit theorems for proportions. Okay. To give you an idea what a proportion would be like, it would be the proportion of people who smoke versus the portion of people who don't smoke. Let's see, the proportion of people who are male versus the proportion of people who are female. Let's see, so when we talk about proportion, we're just talking about like two things. You're either one or you're the other. Okay, that way we have two numbers here. Now, if you read it, it says, suppose x is a random variable with a population proportion p. Okay, so this is population proportion. And again, we select samples of size n. Then we could go ahead and do the same exact thing that we did for means. We're going to pull samples of size n. We're going to find the proportion of that sample. Some are going to be overshoots, some are going to be undershoots, some are going to be about exactly equal to p. And when we find their average, what we find out is the proportion. Now here, we use p hat. This is the sampling distribution. So for p hat, the average for p hat is equal to the population proportion. Okay? Very much like the central limit theorem for means. The average for the sampling distribution, this is the average for the, still the sampling distribution just for proportions, should be equal to the population proportion. Now, the standard deviation for p hat is equal to square root of p q divided by n. Remember, q is just 1 minus p. It's the complement of p. You could write that over here. Q is equal to 1 minus p. Sometimes you may see this formula written as the square root of 1 minus p times p divided by n. That way you don't have to go ahead and calculate q, even though you're calculating right there. Either one you could use. But this is exactly the same thing as the central limit theorem. Now, the only real difference is when in the central limit theorem for means, it says the sample size has to be greater than 30. Let's see, the sampling distribution for p hat is approximately normal. Now, we also have to have when n is large, but also when p, so the population proportion is not too close to 0 or 1. So if you had a room full of people who were non-smokers, and let's say there was 100 people there, and only one of them was a smoker, well, the chance of you being a smoker, the proportion in that room would be 0.01. That's really close to 0. Okay? So we can't use this if the population proportion is really close to 0 or really close to 1. Other than that, the work is essentially the same. You get your population proportion, you find your standard deviation, you plug everything into normal CDF, and get your probability. Okay, so if we're looking at this example, if you're looking at my notes, it says, based on past experience, The bank claims that 7% of people who receive student loans will not make payments on time. Now, 7% is kind of low. When they say too close to zero, that's very ambiguous. You'd have to, I don't know, learn more statistics to find out what too close to zero or too close to 1 is. There is probably a precise definition. I don't know that definition myself, but we're going to say 7 is far enough away from 0. So, banks claim that we've got a population proportion of 0.07. So 7% of the people who receive student loans will not make payments on time. As you can see, there's only 2 options. You either make your student loan payments on time, or you don't make your student loan payments on time. Now, suppose that the bank recently gave out 300 student loans. What is the mean of the proportion of students in this group who may not make timely payments? What is the average of the proportion of students? Okay? So we want a number here. We want an actual number. You just multiply them. I don't have my calculator. So I'll write it out. Oh, that's on average. Okay, here's what they're asking. They're asking the same thing. Mu of p hat. Mu of p hat here is equal to 0.07. Out of these 300, that's how many people you would expect not to pay it. What is the standard deviation of proportion of students in this group who may not make timely payments? So the standard deviation for p hat, if you recall the formula, is p, so 0.07, times 1 minus p. So 1, you could think of it as $1. $1 minus 7 cents is 0.93. So you could come over here and calculate. Q is equal to 1 minus 0.07. Well, that's 0.93. Divided by the square root of 300. Now, this is going to come out to be some decimal number. Square root 0.07 times 0.93 divided by 300. 0.014. We'll stop it there. 0.014. Okay. So now what we can do, what we can say is that our random variable here, random variable x, is approximately normal with proportion, this is our mean, 0.07, comma, here's our standard deviation, 0.014. Okay, so that's all the information we need. Again, this is very much like the previous problem we did. All we had to do was find our mean and find our standard deviation. Using those formulas, the mean should always be the same as whatever the population is, and this is the only thing you have to really change, is the standard deviation. What is the probability that over 10% of these students will not make payments on time? Okay, so here's our normal distribution, 0.07, and then somewhere over here is 10% or 0.1. What is the probability that over 10%, so we want that area right there, because that would be over 10%. So we want to find this area. We're just going to use normal CDF. Well, our lower bound is 0.1. Our upper bound, 100, some really large positive number. Our mean, and now our standard deviation. You do not have to divide this one by the square root of 300. We already did that on the previous step. This is the correct standard deviation you should be using. Okay, so don't divide it by square root of 300 again. So now normal CDF, 0.1 to 100, 0.07, 0.014, and I hit paste, you hit enter, and you get an answer of 0.016. So about 1.5% of students, or about 1.5% chance that your sample proportion will be greater than 10%. Okay, and that concludes 7.1. Okay, in 7.3 we're going to talk about when to use the central limit theorem as opposed not to use it. Here we were learning how to use it. Okay.